In this video, we are going to look at a subject very closely related to calculus, used in solving very hard sequence problems and summation using methods similar to our calculus or infinite calculus, because we are going to generalize our idea of infinite calculus to finite calculus, or you can say discrete calculus. So let's start with problem of polygonal numbers. So you can see in the picture, polygonal number are number of dots or points needed to make a regular polygon of some side length. For example, to make a triangle of side length 2 dots, we have to use minimum 3 dots. You can see in the picture also. And if I want to make a hexagon of side length 3, so I must have at least 15 dots, and we have to find the formula for any polygonal number of some given side length n and polygon of side A. You can also notice that in all the polygonal sequences, the first term is always 1 and the next term is the side length of that polygon. For example, the next term of triangular numbers is 3, which is the sides of triangle, and similar for hexagons. To solve this problem, let's start with finite calculus. Like in our calculus, we first define what is a function. So in finite calculus, let's again define a function. So a function is just a mathematical object which takes an integer as an input and outputs another integer. In our infinite calculus, functions can return any real number, but in finite calculus, our function only returns an integer. For example, f of n is equals to n square minus 1. It will always return an integer if n is an integer. And in our infinite calculus, we define some operations like differentiation and integration on functions. So similarly, we also define derivatives or differentiations of our function in finite calculus. And differentiation gives us rate of change. So similarly, we define difference operator or delta, which just gives us difference between f of n and f of n plus 1. We can also define delta square or double differentiation operator, which takes difference of difference. For example, if s of n is equals to n square, so delta of s of n will be 2n plus 1, and double difference operator on this will be equals to 2. Similar to our infinite derivatives, our difference operator is also distributive under addition, and we can take out our constant terms multiplied by the function while taking its difference. So now let's try to define power rule for our finite calculus. So we know that in our infinite calculus, the differentiation of x to the power n is just n times x to the power n minus 1. But it is not valid for our finite calculus. So to define it, let's define another operation on numbers which we call factorial powers, which is defined as n to the power factorial power m is just n times n minus 1 times n minus 2 till n minus m minus 1. For factorial powers, we underline our superscript, which is m, and we can define our power rule for finite calculus using factorial powers. that difference of x to the factorial power n is equals to n times x to the factorial power n minus 1. And we know that in our infinite calculus we define something called integrals, which is just inverse of derivatives or antiderivatives. We can define our similarly integrals for finite calculus, which will be the inverse of difference operator, and our difference operator is calculating difference. So our integrals for finite calculus are summations or summation operator, which is denoted by sigma from Greek alphabets. And similarly, we can define power rules for our summation operator, which is summation of x to the power factorial power n is just x to the power n plus 1 factorial power divided by n plus 1 and plus c. So we don't have to forget our plus c in here also. So now we are ready to formalize our fundamental theorem of finite calculus, which is if summation of f of n is equals to capital F of n, then summation of from a to b f of n is just f of b minus f of a. So now let's get back to our polygonal numbers. So let's list our polygonal numbers for triangle and squares in a table. So you can see that for n is equals to 1, triangular number is 1 and square number is 1, then 2 is 3, 4 and so on. So now if I calculate the difference of consecutive terms in each column, or you can say if I apply difference operator in each column, we will get a increasing arithmetic sequence. And if I again apply difference operator, we will get a constant term. So we can write it as the double difference or double difference operator on our polygonal number is a minus 2, where a is the side of polygon. For example, in triangular number, a is equals to 3, which is the side of triangle. So our double difference is 1, which is 3 minus 2, and similar for square. So now let's try to solve this finite differential equation for a pentagonal number. So for pentagonal number, side length is 5, for which means a is equals to 5. So double difference will be 5 minus 2 or 3. So if double difference is equals to 3, so using some hit and trial or some intuition, we can write the single difference will be equals to 3n plus some constant a, which looks very similar to integrating it. So if I again finite integrate, or which is very difficult to do in general because it requires very much intuitions, so our p5 or polygon or pentagonal number will be equals to 3n square by 2 plus a minus 3 by 2 times n plus some other constant b. And we know that the first polygonal number is just 1 and second polygonal number is just the number of side lengths of that polygon. So p1 will be 1 and p2 will be equals to 5 for pentagon, as you can see in this image also. So now we have the formula for pentagonal number in terms of two constants. So using these two conditions, we can find the value of these two constants a and b using these two equations, and we will get a is equals to 1 and b is equals to 0, which means our polygonal number for side length 5 or pentagonal number is just n by 2 times 3n minus 1. Not only solving polygonal equations, we can also find the value of some very hard sequences which are very difficult to find. So let's look at how we can find the value of summation of n to the power 4. So we know that we can integrate a factorial power, but we cannot integrate directly our normal ordinary exponential powers. So if I can write my n to the power 4 are ordinary powers as the sum of factorial powers, then I can integrate it. And there is a very famous formula to write n to the power m as summation of sum of some factorial powers with some coefficients in curly braces m and k. These coefficients are very similar to binomial coefficients, but they are not binomial coefficients. They are called Stirlings number. We can also write these Stirling numbers similar in triangular form, which is very similar to Pascal's triangle. So if we want to write n to the power 4, so you can see in this image of Stirling's number, for n is equals to 4, we have to look at the fourth column and use these numbers as coefficients. So we can write using this table n to the power 4 as sum of factorial powers. So we can write it as in this form, and now we can directly integrate it or finite integrate it. Just increment the power and also put them in denominator, and if you expand all the things and factorial powers and simplify this, you will get this formula, which is the general formula of summation n to the power 4. So in this video I've shown you how powerful is finite calculus for calculating different summations and techniques. So if you want more videos like this one, you can subscribe to our channel and share with your friends. Also, if you have any thoughts about this, you can comment down below.